Hi guys again. Here I'm going to cover examples on shear design, which is part two. There's going to be another part. It's going to be a rather lengthy example. I'm going to provide that to you sometime, hopefully on Saturday. But for now, I'm going to start with this example. So here what I have is a rectangular beam and is designed to carry a shear force V ultimate of 120 kilonewtons. No web reinforcement is to be used, which means I just want it to be based on the shear strength of concrete. What is the minimum cross section if controlled by shear? And F prime C is 22, and I'm using D is equal to 2B. Now, we said if V ultimate is less than 5.083 lambda square root F prime C B web V, then there's no AV required. So I'm just going to make V ultimate equal to this right here, which means BW times D is going to be equal to 120 times 1,000 to make that into Newton. Divide that by 5.75 and the 0.083 times, again, using normal weight concrete, so lambda is equal to 1 times square root of 22. So this is the total area in millimeters squared. Using D is equal to 2B. I get D to be almost 906 millimeters and B web almost 453. Again, this is just for comparative reasons, so I'm not going to give you a full cross section, but with 906, probably H will be maybe around a meter. BW probably will be around half a meter. So we're talking about 1 meter times half. Now, if I'm using just the minimum reinforcement, just the minimum, okay, then D will reduce to about 633. So you can see that there's quite a drop. And B is going to almost 316.75 millimeters. So just a little bit of reinforcement saves me a lot on concrete. So the whole point of this example, just to show you the difference between using reinforcement and not using reinforcement. Moving on to the other example. Now here I have a simply supported rectangular beam. It's 40 centimeter wide. It has an effective depth of D equals 63.4. The total height H is 70 centimeters. It carries a total factor load of 140 kilonewton per meter. So pretty much what I have, this is my beam right here. And I have a distributed load. And my drawing is not up to par, but hey, this is what I have. So this is 140 kilonewton per meter, all right? And the span, clear span, is 60 meters. So this is what we have. This is my 60 meters. All right. It's reinforced with 4,532. So the cross section is something like this. Here I have 4,532. This is my D, which is about 63.4. And this is my B web, which is equal to 40 centimeters. So here we have 4,532. It continues uninterrupted into the supports. So that means that the 4,5 starting from here and over here. It starts here and goes all the way to here. So no interruption, just 4,532. F prime C is equal to 22 megapascal. What part of the beam is reinforcement required? Use vertical phi 10 U stirrups, that's what he wants, and Fy is 420 megapascal where reinforcement is needed. Okay, so to start off with something like that, what we usually need to do is we need to find what V ultimate is, right? And since this is a simple beam, and again, here we're going to calculate V ultimate at D from the support. So that would mean that V ultimate would be equal to 140 times 6, which is, this is your W, this is your L. So I'm basically saying it's WL over 2 minus W times D, all right? So that will be minus W times D, and that will give me the V ultimate, which is 331.24 kilo in Newton. All right, now I need to know whether I'm going to require reinforcement or not, so I need to calculate phi VC. As I said, I can use either phi VC equation A, or I could use phi VC equation B. In doing so, I calculated for equation A, and that was phi, this is my 0.75, 0.17, lambda is equal to 1, square root of 22, times my B is 400, times D 634. So this is my phi VC, 151.7 kilonewtons. Now, if I use equation B, I'm going to use phi 0.75, which is constant, 0.66, lambda is equal to 1. Now this right here is simply area of steel divided by B times D, which is my roll web. Okay, so the area of steel is going to be the area of the 4532. This is my 400 and D is my 634. So you will get this number right here. Square root of 22 times 400 times 604, and here I'm getting 137.3 kilo Newton. So you can see there's quite, well, I mean, there's some difference between equation A and equation B. Again, here I can either use the 151 or I could use the 173.3 according to the code. So if I actually used the larger value, there's nothing wrong with that. All right, but as I said, preferably for me, I'm going to use the smaller values, and that's going to be the 137.3 kilonewton. All right, so this is now my phi VC, so I'm sticking with phi VC equation B, and I'm not using phi VC equation A, which was the old simple shear equation. Okay, so in this figure I'm showing the shear diagram, or actually I'm showing half of the shear diagram since it's symmetric about the center line. Now the value here is my V ultimate, which was equal to 331 kilonewton. This is my phi VC, which was 137.3 kilonewton, which came from equation B. And this value here is the 0.083 lambda square F prime C times BW times D, because as we said, we had three zones. Zone 1 is when V ultimate is larger than phi VC, and then we had V ultimate less than phi VC and larger than 0.083, which is right here. So now in this portion, this area right here, this is where shear reinforcement is required, because V ultimate is larger than phi VC. And the distance that I calculated was at 2 meters almost. And the way that I did this, I said, well, I need to know when the value of the shear is 137.2. So this probably would be equal to WL over 2, which is my reaction here, minus the slope of this curve, which is simply W minus 40 times X. So the only unknown is X, and that will give me 202. The way that I calculated the 2.46 was, again, this value here is equal to 74.05, so I'm just going to replace the 137.2 with this value. The only unknown is X, and you get 2.5 meters. So these are my three distinct zones required here, minimum, and after this line, not required. Okay, so continue now with the calculation of the spacing. I'm going to start with the required, obviously. So Vs is equal my V ultimate minus my phi VC divided by phi, and this gives me 258.56 kilonewtons, which is less than the maximum Vs allowed, which is 0.66, and also less than 0.33 square root F prime C B web times D. And this information I use for the first two spacing. because if this was not so, then this will be 300 and this would be d over 4. But since it is less than 0.33, though it will become 603.17 millimeters. Now I'm using phi 10 stirrups, then the AV, or the cross-sectional area, is equal to 2 times pi 10 squared over 4, which is 157.08. Again, this is my U, so this is my first leg, and this is my second leg, hence the 2. Okay? Now, spacing at this point will be equal to this area, 157, times Fy 420, times D 634, divided by Vs, which is 258.56 times 1,000 to convert that into newtons, and then I'm getting 161.77 millimeters as my spacing. And the other spacing that I need to check is the one that comes from the minimum AV. Okay, this is my minimum AV that I need to provide. So S1 max is AV minimum. Again, I'm choosing phi 10 as my stirrup. So this is still my 157.08. I'm using 420 as my yield for the steel, divided by square root of 22 times B. So this is my area 567, and the other S2 max is 471. So out of the 4 that I have, the minimum obviously is 16.1 something. I actually could use 16, but here I elected to use 15 centimeters. Might be easier for them to mark it on the longitudinal reinforcement. Now, what is kind of new odd here is I use it only for the first meter, knowing that we need reinforcement up to 2 meters. But what I did to come up with the 20 centimeters over here is I calculated V ultimate at 1 meter from the reaction. Okay. Sorry, this is really not easy to write with. Anyways, now this value will give me a V ultimate around 280. So if I use that value 280 and calculate a new S, this will give me 20 centimeters. So I'm kind of saving on the number of stirrups that I'm using for the second meter. All right. So now for the required, or the minimum that we said was until 2.5, we have the minimum, which was D over 2, which was this 30 centimeters. So what is left is like another half a meter. So I just chose to use 30 centimeters for the last meter as well. So that will cover both the minimum and the area that I'm not required to provide any shear reinforcement. So by doing so, I really need not to check equation C, because I'm already providing a minimum area of steel. Also, I don't need to have any transverse reinforcement because D is larger than my B web. So this probably would be my final design. I'm going to use 1 phi 10 every 15 centimeters for the first meter, then 20 centimeters for the second, and then 30 centimeters for the last meter. Okay, and then obviously this is going to happen on the other side of the center line as well. So this will be the end of this example. I'm going to do another one. Here I'm actually drawing it part of column, and just to show you that we only take D from the face of the column. So that's the difference between this example and the example before. Again, I'm using the same cross section, but here I'm using different loading. Dead load 24 kilonewton per meter, live load is 30. I'm using smaller F prime C. Here I'm using 280 for my stirrups, and I'm using phi 8 instead of phi 10. Okay, like the example before, I still need to calculate my V ultimate. So now W ultimate is 1.2 times 24 plus 1.6 times 30, so this would be my 76.8 kilonewton over per meter. All right, the distance is 8, so this is my W times L over 2 minus W times half of the column plus D Again, I'm going from the center of D, so this is equal to 243 kilo Newton, because as you see, the load started at the middle or at the half of the column. So now this is my V ultimate. Again, here I'm calculating both phi VC. This is equation A, and I'm getting here 148.64. From equation B, I'm getting here 134.58. Since I'm using again 432, the rho W is not going to be any difference. Again, here I went with the smaller value of 5VC, and I want to emphasize, if you guys elected to take 148.64, it is absolutely correct. All right. So calculating VS, it's going to be my V ultimate minus 134, which is my 5VC divided by 7.5, and this is giving me 144.56, which again is less than 0.66 and 0.33. So going now to the spacing, still I'm going to use 600. D over 2 is 318 millimeters. For phi 8, again, it's U stirrup, so we have two legs, hence the 2 over here. This is leg number 1, and this is leg number 2, so this will be 100.53 millimeters square. Based on that, I can calculate the spacing, and I'm just putting in the AV. FY now is 280 instead of 420. This is 636, and the spacing is 123.84 millimeters. Okay, now S1 max and S2 max. And these are the, like I said, if you're using AV, then these need to be satisfied. One is 247 and the other is 201.6 millimeters. Based on that, the smaller one is what is 123.84, so I probably have to use this one. So again, the 2.25, I'm going to leave that up to you to calculate it, but you can use the same equation that I used before. So I'm going to be required to use up to 225. So I'm using 1 phi 8 at 12 centimeter for the first 1.5 meters. Okay, and then at 1.5 meters, again, I calculated a new V ultimate. All right, and that given me an S actually bigger than 20 centimeters. But again, going back to the S1 max and S2 max, the minimum of that was 20 centimeters, right? So I'm using 12 for the first 1.5 meter, and then I'm using 20 from 1.5 to 3.1. The only reason why I said I'm not going to use stirrups for the last 90 centimeters is to show you how I'm going to calculate equation 5VCC. So as you know, in that equation, we have the shape factor, or the size factor, I'm sorry, and that's square root of 2 over 1 plus 0.004D. So again, this should never be more than 1, so it's 0.75, so I'm going to use that. So this is my phi, this is my 0.66, this is this one right here, this is the size factor, this is rho W again, I'm using the same for phi 32, this is square root 21, B web and D, and here I got 100.93 kilonewton. So when I calculate V ultimate at 3.1 meters, it's 69.12. All right, which is less than 72.3, which is also less than 100.93. So this entitles me not to use any stirrups at the last 90 centimeters. But you have to know that sometimes, maybe due to the shifting of the loads or some unexpected value, I would also recommend to add stirrups at the areas where it is not required. And that will finish the examples. Again, I will add another example, and I think that example is going to be a little bit more involved than these two, but just to give you an indication of how to use or how to design for shear. And hopefully I will have that up either Saturday or Sunday. And have a good day.